In some movies it seems relatively easy to open door during the flight. You have to rip off some cables and the door will simply jump out of the frame, which is smaller than the door, but the door fits through the frame anyway, no problem. There are some sparks and some fire and some effects, and finally the door is open, they jump out and they take a parachute and they fly into freedom. Well, it's not that easy, as I will show. An aircraft door, a passenger door of a passenger airplane. Okay. Looks like this. So that's the fuselage. Oops, that way. If you want, there are the wings. And the door has about a shape like this. And the air pressure inside the airplane presses the door into its frame, like that. Now the question is, for example at 10,000 meters, how much is the pressure outside and how much is it inside? And then we know the difference. We can calculate the area of the door, and we can calculate the force that you would need to pull this door to the inside, because that's the only way how it opens. Well, of course there are some cargo aircraft with doors that opens to the outside. These doors have very special mechanics to hold them in place, but we are talking about passenger airplanes. Well, to find out the pressures that are inside or outside the airplane at 10,000 meters, I use this original altimeter from an old aircraft. Of course we could consult some tables and look at them what all the pressures are in different altitudes, but I think that's a little bit boring. So let's play with this altimeter. I will put it into my vacuum chamber here. It's a plastic chamber with a cover and a manometer that tells us the pressure inside, and I put this altimeter here to check what pressure we have when we reach 10,000 meters, or because this altimeter here is calibrated in feet, it's about 30,000 feet. Well, it's not exactly 30,000, but I think for our experiment this is close enough. We are now at 1,300 and about 50 feet. Of course, this altimeter measures in fact the air pressure. So the altitude here on my desk changes depending on the weather. If we have high pressure weather, it will show us a lower altitude, and on low pressure weather it will show us a higher altitude. And this knob here is to adjust for this for the atmospheric pressure. The pressure is indicated in the little window right here. This is in millimeters or inches of a mercury column. So we have now 30 point something inches. I could get the exact value from the weather forecast. Of course, I had to convert it into inches of mercury, because normally here in Europe we are working with hectopascals. But well, I know that we are on 1350 feet, so I can set that to our actual altitude. So I put it inside my chamber. I only have to connect my vacuum pump. So let's see. I connect it here on this valve. Close the valve. Okay, let's see what happens. I open the valve now. You can hear the pump sounds different, so we are already on 2000, 3000, 4000 feet. I have to wait until it goes up to 30,000. 7. We can go a little bit faster. 9, 10,000. 12, 13. That's of course faster than any airplane would climb in the world. Well, maybe a jet fighter of some sort. 20,000. But I think even those are not that quick. 25, 25. So I go a little bit slower. 29 and oops, a little bit. Come on, yes. Well, it's a little bit difficult, but I think that's about it. 30,000 feet. Or 10,000 meters, more or less. So I disconnect my vacuum pump. Maybe we can let a little bit air inside. Yes, that goes, and yep, now perfect, on spot. I hope you can see that in the camera. That's 30,000 feet. Now the pressure gauge here. I have to put my lamp on. Let's see if we can zoom on that. Oops. We have 0 is about here. Let me. That's 0. That means our normal pressure here on ground. We have minus 0.5 bar. That's minus 1 bar is 1 kilogram per square centimeter. So it's minus 0.6, minus 0.7, not exactly. Well, it's a little bit difficult to read this. It's also not a very precise manometer, but I think 0.6, 0.65, well, 0.68. Let's write that into the sketch. So we have minus 0.68 bar outside. Oops, you can see. So, as I wrote it here, minus 0.68 bar outside the airplane. Now, the problem is inside the airplane is not the same pressure as on ground. Inside the airplane, a pressure of about 2000 meters is sustained. So why don't they put the same pressure inside as on ground? Well, it's simple. 2000 meters are not a problem for any passengers, but it relieves the fuselage from well, I would say 20% of the stress of the pressure stress. Okay, now we have to find out what pressure it is on 2000 meters. 2000 meters, that's about 6000 feet. So here we have 30,000 feet. Well, that's not exact, but I think it's close enough. It's 3 point something feet for a meter. So let's see what we can do. I open the valve, I let some pressure into my chamber until we are on 6000 feet. So we are descending rapidly. Do we have 20,000? The triangular pointer or the 10,000 feet. So 15, 14, 13, 12, 11. That's 10,000 now, and we go lower. 9, 8, 7, oops, and careful, and 6,000 feet. That's the cabin pressure. And as we can see on the manometer, it is not 0, it is 0.1.15, huh? About that. 0.15 bar. Negative pressure minus go back to my sketch, minus 0. What did I say? 15 bar. Okay, I think that's it. So I release the vacuum. And our altimeter should read about the same value as before. It does not, because, well, it's a mechanical thing, it's very old. We can tap it a little bit, but yeah, we are close enough. 10 feet, no, 100 feet, maybe 200 feet off the center, but okay, that's good enough. Okay, so we do have 0.68 bars on the outside, 0.15 on the inside, and 1.5 in the inside. Makes a difference of 3, 5, 0, 0.53 bar. So we can say, because this is all rough calculation, about 0.5 bar difference from inside to outside. Half a bar. That means on this door, on every square centimeter, it's about that much, is half a kilo of pressure. Okay, so let's say this door, a normal passenger door, with a handle somehow, is, let's say, 1 meter wide, and let's say 180 high. Now, since I'm not so good in manual calculation, I take my very reliable HP 11C pocket calculator, which is now about 20 or more years old. Well, I think it's about 30 years old, and in fact it needed, I think, 3 times new batteries in all this set. So one set of battery is good for about 10 years and no other problems with it. This is probably the best calculator you can have, and well, you could have, because it's not produced anymore. Okay, 1 meter by 1 meter 80 makes, oh, I don't need a calculator, 1.8 square meters for this door. Now, 1 square meter is 100 by 100 centimeters, of course. So that means it's 10,000 square centimeters. So we have 18,000 square centimeters. Okay. Each one with a 500 gram pressure on it. Oops, I have to move the camera. So, half a kilo on 18,000 square centimeters. That means 9,000 kilogram of pressure here, from inside to the outside. So that means, oh, this is really a rare occasion No, it does not. There was a blinking star here on the display that indicates me that it is time to change the batteries. Well, I think 10 years over. We have to renew the batteries, but now it's not blinking anymore. Okay, maybe it runs for another 5 years. Okay, so that means to open that door to the inside, you need a strength to pull 9,000 kilos. I doubt that the handle here would be stable enough to do that. It would simply break and the door remain in place. So you have absolutely no chance to open that. That's it.